In the previous classes, you learned the basic concepts of coordinate geometry, like plotting different points in a two-dimensional plane using their coordinates or distances from the x and y axes. You also learned some important formulae, like the distance formula that gives the distance between two given points. For example, consider 2 points with coordinates -3, 4 and 3, 6. Using the distance formula, the distance between the two given points comes to 2 under root 10. You also learned the formula for finding the coordinates of a point dividing internally a line segment joining two given points in a given ratio. For example, consider a point C dividing the line joining points A and B in the ratio 2:3. By the ratio formula, the coordinates of C are -3 by 5 and 24 by 5. Suppose point C is the midpoint of the line joining the given points A and B. In this case, the coordinates of point C are given by x1 plus x2 by 2 and y1 plus y2 by 2. By the ratio formula, the coordinates of point C in this case are 0 and 5. You also learned the formula to calculate the area of a triangle whose vertices are given. For example, consider triangle ABC. Substituting the values of the coordinates of the vertices in the formula, the area of triangle ABC comes to 4 square units. Now, consider the case where points A, B and C lie on the same line or are collinear points. Applying the formula, we find that if points A, B and C are collinear, then the area of triangle ABC is 0. We can also say that if the area of a triangle ABC is 0, then A, B and C are collinear points. We come across many different kinds of lines in our daily life, like horizontal lines, vertical lines, and inclined lines. Generally, we call a line an inclined line when it makes an angle with the horizontal. The same idea of the slope of a line can be extended to coordinate geometry. A line intersecting the x-axis forms supplementary angles. The angle made by a straight line in the anti-clockwise direction with the x-axis is called inclination. Here, the anti-clockwise direction is also called the positive direction. The x-axis and the lines parallel to it are called horizontal lines. If line AB lies along the x-axis or is parallel to the x-axis, then its inclination is 0. The y-axis and the lines parallel to it are called vertical lines. If line AB is parallel to the y-axis or perpendicular to the x-axis, then its inclination is 90 degrees. The inclination of a line can have a value anywhere from 0 to 180 degrees. If theta is the inclination of a line, its slope or gradient is given by tan theta. The slope of a line is represented by m. The slope of a horizontal line is 0. The slope of vertical lines is not defined. Let us learn how to find the slope of a line passing through two given points. Let P, x1, y1 and Q, x2, y2 be 2 points on a non-vertical line L, whose inclination is theta. Since the line is not a vertical line, x1 is not equal to x2. Hence, theta may be an acute angle or an obtuse angle. First, let us consider the case when theta is an acute angle. Draw perpendiculars QR and PT from Q and P onto the x-axis. Draw perpendicular PM from P onto QR. Since QR is perpendicular to both the x-axis and PM, we have PM is parallel to the x-axis. Since PM is parallel to the x-axis, angle QPM is equal to angle QSX or theta, since they are corresponding angles. In right angle triangle PMQ, tan theta is equal to QM upon PM. Let this be equation 1. Now, QM is equal to QR minus MR or Y2 minus Y1. Let this be equation 2. Also, PM is equal to TR. This means PM is equal to OR minus OT or X2 minus X1. Let this be equation 3. Substituting the values of QM and PM from equations 2 and 3 in equation 1, we get the value of tan theta as Y2 minus Y1 upon X2 minus X1. Now consider the case when inclination theta is an obtuse angle. Draw perpendiculars QR and PT onto x-axis. Draw perpendicular PM from P to QR and extend MP to S. Since QR is perpendicular to both the x-axis and PM, we have PM is parallel to x-axis. Since PM is parallel to the x-axis, angle QPS is equal to angle QUX or theta, since they are corresponding angles. Since angle QPS and angle QPM are supplementary angles, and angle QPS is equal to theta, angle QPM is equal to 180 degrees minus theta. We can also say that theta is equal to 180 degrees minus angle QPM. Thus we get slope m of the line is equal to tan theta, which is equal to minus tan of angle QPM. Let this be equation 1. In right-angled triangle PMQ, tan of angle QPM is equal to QM upon PM or QM upon RT, since PM is equal to RT. Putting the values of QM and RT in terms of the coordinates of P and Q, we get equation 2. From equations 1 and 2, we get slope of the line is equal to y2 minus y1 upon x2 minus x1. Thus we see that whether the angle of inclination is acute or obtuse, the slope of a line passing through two given points is given by the same formula. Let us see if there is a relationship between the slopes of parallel lines. Here are two non-vertical parallel lines, L1 and L2, having inclination alpha and beta, respectively. If lines L1 and L2 are parallel, their inclination must be the same. Thus, we can say that angle alpha is equal to angle beta. Since angle alpha and beta are equal, tan alpha is equal to tan beta. By definition, tan alpha and tan beta represent slopes M1 and M2 of lines L1 and L2. Thus, we can say that if two non-vertical lines are parallel, their slopes are equal. The converse is also true, that is, if the slopes of two non-vertical lines are equal, the two lines are parallel. Now, let us find the relationship between the slopes of perpendicular lines. Here are two perpendicular lines, L1 and L2, having inclination alpha and beta respectively. Since line L1 is perpendicular to line L2, and line L1 makes an angle alpha with the x-axis, angle beta is equal to angle alpha plus 90 degrees. Let us take the tangent of both the sides of the equation. Tan alpha plus 90 degrees is equal to minus cot alpha. Also, cot alpha is equal to the reciprocal of tan alpha. Now, tan alpha and tan beta represent the slopes of lines L1 and L2 respectively. Putting these values in equation 1, we see that slopes of two perpendicular lines L1 and L2 are the negative reciprocals of each other. We can also say that the product of the slopes of two perpendicular lines is equal to minus 1. The converse is also true, that is, if the product of the slopes of two lines is minus 1, the two lines are perpendicular to each other. In this module, you will learn to find the angle between two lines when their direction ratios, direction cosines, vector equations, or Cartesian equations are given. Consider two lines, L1 and L2, passing through the origin as shown. Let theta be the acute angle formed between lines L1 and L2. You will learn to find the value of this angle theta using the direction ratios, direction cosines, vector equations, or Cartesian equations of the two lines. Consider a point A on line L1 and a point B on line L2. Now, consider the directed lines, OA and OB, representing the position vectors of points A and B, respectively, with respect to the origin. Let A1, B1, C1, and A2, B2, C2 be the direction ratios of lines L1 and L2 respectively. Thus vectors OA and OB can be written in component form as shown. We know that the cosine of angle theta between two vectors is given by their dot product divided by the product of their magnitudes. The dot product of vectors OA and OB is equal to the sum of the products of their corresponding components as shown here. The magnitude of vector OA is equal to under root of A1 square plus B1 square plus C1 square. Similarly, the magnitude of vector OB is equal to under root of A2 square plus B2 square plus C2 square. Substituting the values of the dot product of vectors OA and OB and their magnitudes in the expression for cos theta, we can find angle theta between lines L1 and L2 in terms of their direction ratios. Let this be equation 1. Now, we will find the sign of angle theta between vectors OA and OB. From trigonometric identities, we know that sin theta is equal to under root of 1 minus cos square theta. On simplifying, we get the expression for the sign of angle theta between lines L1 and L2. Let this be equation 2. These equations lead to some interesting observations. If lines L1 and L2 are perpendicular to each other, then the value of theta is 90 degrees and cos theta is 0. Equating the value for cos theta to 0 from equation 1, we get the condition for the perpendicularity of two lines. If lines L1 and L2 are parallel to each other, then the value of theta is 0 degrees and sin theta is 0. Equating the value for sin theta to 0 from equation 2, we get the condition for two lines to be parallel as shown here. The given lines L1 and L2 may not always pass through the origin. In such a case, we find the angle between them by considering lines L1' and L2' that are parallel to L1 and L2 and pass through the origin. Now, let us see how we can find angle theta if we are given the direction cosines of lines L1 and L2 instead of their direction ratios. If L1, M1, N1 and L2, M2, N2 are the direction cosines of lines L1 and L2 respectively, then from equation 1, cos theta can be written as shown. Let this be equation 3. We know that the sum of the squares of the direction cosines of any line is always equal to 1. Thus, the terms in the denominator of the right-hand side in equation 3 is reduced to 1. Equation 4 gives us the equation for the cosine of angle theta between lines L1 and L2 in terms of their direction cosines. Replacing the direction ratios with direction cosines in equation 2 and simplifying, we get the equation for the sine of angle theta between lines L1 and L2 as shown here. Now, we will find the angle between the two lines when their vector equations are given. Let us represent the two lines L1 and L2 with their vector equations. Let the vector equation of line L1 be vector A1 plus lambda into vector B1. Similarly, let the vector equation of line L2 be vector A2 plus mu into vector B2. The cosine of angle theta between the two given lines is equal to the modulus of the dot product of vectors B1 and B2 divided by the product of the magnitudes of the vectors B1 and B2. Let us now find angle theta using the Cartesian equations of lines L1 and L2 shown here. From the Cartesian equations of the given lines, we get that A1, B1, C1 and A2, B2, C2 are the direction ratios of the two lines. Thus, the cosine of angle theta between the lines given in Cartesian form can be found using the formula shown. We know that the graphical representation of a linear equation in two variables is a straight line. In the coordinate system, such linear equations are called equations of lines. Equations of lines have different forms such as point-slope form and two-point form. Let's consider points P1, 1 and Q2, 3. Can you say which point lies on the given line? Let's extend the line. We see that the line passes through point P1, 1. Let's verify this algebraically. On substituting the coordinates of the point in the given equation, we see that the values of the left-hand side and the right-hand side are equal. In other words, point P satisfies the equation of the line. However, point Q2, 3 does not satisfy the equation of the line. Hence, for a point to lie on a line, it must satisfy the equation of the line. Now consider point P lying at the intersection of the two lines. Each of these two lines is represented by an equation. As the point of intersection, P lies on both the lines. Its coordinates must satisfy the equations of both the given lines. By solving these two equations, we get the point of intersection. Let us verify whether the coordinates of P, 5 and -8 satisfy the equations of both the lines. Substituting the coordinates of P in equations 1 and 2, we observe that the equations are satisfied. Let us start with equations of horizontal lines or lines that are parallel to the x-axis. Consider a horizontal line L that intersects the positive side of the y-axis at a distance a from the x-axis. The y-coordinate of every point on line L at any position is a. Thus, the equation of line L is y is equal to a. Consider another horizontal line S that intersects the negative side of the y-axis at a distance a from the x-axis. The y-coordinate of every point on line S at any position is -a. Thus, the equation of line S is y is equal to -a. Now let us find the equations of vertical lines or lines that are parallel to the y-axis. Consider a vertical line L that intersects the positive side of the x-axis at a distance b from the y-axis. The x-coordinate of every point on line L at any position is b. Thus, the equation of line L is x is equal to b. Consider another vertical line S that intersects the negative side of the x-axis at a distance c from the y-axis. The x-coordinate of every point on line S at any position is -c. Thus, the equation of line S is x is equal to -c. For example, consider point P. The equation of the horizontal line L passing through point P is y is equal to -5. So in general, the equation of any line parallel to the x-axis or a horizontal line passing through point P, h, k, is y is equal to k. The equation of the vertical line S passing through point P is x is equal to 4. So in general, the equation of any line parallel to the y-axis or a vertical line passing through point P, h, k, is x is equal to h. The equation of a line passing through a given point and having a given slope can be represented using the point-slope form. Consider a non-vertical line, L, passing through a given point, P x1, y1. Let M be the slope of line L. Let A x, y be any arbitrary point on line L. Recall the formula for the slope of a line passing through two given points. According to the formula, slope M of line L passing through points A and P is given by y minus y1 divided by x minus x1. From the formula for the slope of a line, we get equation 1. A point A can lie on line L only if its coordinates satisfy equation 1. Equation 1 represents the point-slope form of the equation of a line passing through a given point x1, y1 and with slope m. For example, consider a line L passing through a given point P of 1, 4 and having a slope 3/2. Let us put the values of m and the coordinates of point P in the point-slope form of equation of a line. On simplifying, we get the required equation of the line as 3x minus 2y plus 5 is equal to 0. The equation of a line passing through two given points can be expressed in the two-point form. Consider a non-vertical line L passing through two given points P and Q. Let A be any arbitrary point on line L. Recall that 3 points are collinear if two lines passing through any two pairs of the given points have the same slope. Thus we can say that points A, P and Q are collinear if the slope of line PA is the same as slope of line PQ. Let this be equation 1. The slope of PA is given by y minus y1 upon x minus x1. Similarly, the slope of PQ is given by y2 minus y1 upon x2 minus x1. Let us put the values of the slopes of PA and PQ in equation 1. On simplifying, we get the two-point form of the equation of a line passing through the given points P and Q. For example, consider a line L passing through the points -1, 2 and 6, 4. Let us put the coordinates of the points P and Q in the two-point form of the equation of a line. On simplifying, we get the required equation of the line as 2x minus 7y plus 16 is equal to 0. In this module, you will learn about the slope-intercept form, intercept form, and normal form of the equation of a line. You have already learnt about the equations for horizontal and vertical lines, and the point-slope form and the two-point form of the equation of a line. Suppose a line intersects the x-axis and the y-axis at two distinct points. Let us denote these points as P and Q, respectively. Then length OP is called the x-intercept of the line, and length OQ is called the y-intercept of the line. Note that if OP is equal to A and OQ is equal to B, then the coordinates of point P are A, 0, and the coordinates of point Q are 0, B. The equation of a line having a given slope and either an x-intercept or a y-intercept can be represented using the slope-intercept form. Consider a line L with slope m that intersects the y-axis at a point A, which is at distance c from the origin. This means that the given line passes through the point 0, c. We already know the point-slope form of the equation of a line with slope m passing through a given point x1, y1. Substituting the values of the slope of the line and the coordinates of point A in the point-slope form and simplifying, we get the required equation as y is equal to mx plus c. This is the slope-intercept form of the equation of a line with slope m and y-intercept c. For example, let us find the equation of a line with the y-intercept 2 and slope -2/3. Using the slope-intercept form, the required equation of the line is 2x plus 3y minus 6 is equal to 0. Now, consider a line L with slope m whose x-intercept is given as d. This means that the given line passes through the point d, 0. Putting the values of the slope of the line and the coordinates of point B in the point-slope form and simplifying, we get the required equation as y is equal to m into x minus d. This is the slope-intercept form of the equation of a line with slope m and x-intercept d. For example, let us find the equation of a line with x-intercept 3 and slope -2/3. Using the slope-intercept form, the required equation of the line is 2x plus 3y minus 6 is equal to 0. The equation of a line having an x-intercept and a y-intercept can be represented using the intercept form. Consider a line L with x-intercept A and y-intercept B. Let's denote the points where the line intersects the x-axis and the y-axis as P and Q respectively. Therefore, the coordinates of point P are A, 0 and that of point Q are 0, B. We already know that the two-point form of the equation of a line passing through the given points x1, y1 and x2, y2. Substituting the coordinates of points P and Q in the two-point form and simplifying, we get the intercept form of the equation of a line as x upon A plus y upon B is equal to 1. For example, let us find the equation of a line L making intercepts 4 and 3 on the x and y axis respectively. Using the intercept form, the required equation of the line is x by 4 plus y by 3 is equal to 1. On simplifying, we get the equation of the line as 3x plus 4y minus 12 is equal to 0. The normal form is used to express the equation of a line when we know its perpendicular distance from the origin and the inclination of the perpendicular drawn to the line from the origin. Consider a non-vertical line L. Let OA be the normal or perpendicular drawn to line L from the origin. Let the perpendicular distance of line L from the origin or the length of perpendicular OA be P. Further, let angle AOX be omega. Thus, omega is the inclination of normal OA. Let us draw a perpendicular AM from point A to the x-axis. In the figure, note that distance OM represents the x-coordinate and distance AM represents the y-coordinate of point A. Let us find the values of OM and AM to get the coordinates of point A that lies on the given line. From right-angled triangle OMA, distance OM is equal to P into cos omega, and distance AM is equal to P into sine omega. Thus we get the coordinates of point A as P cos omega and P sine omega. Note that for the given values of P and omega, the coordinates of point A will remain the same no matter the quadrant in which line L lies. Now that we know the coordinates of a point on line L, we can find its equation if we know its slope using the point-slope form. Let M be the slope of the given line L. Since OA is perpendicular to line L, the product of their slopes is equal to -1. Given that the inclination of normal OA is omega, its slope is equal to tan omega. Thus we can say that M into tan omega is equal to -1. This implies that the slope is equal to minus cos omega upon sin omega. We already know the point-slope form of the equation of a line with slope M passing through a given point x1, y1. Substituting the values of slope M of the line and the coordinates of point A in the point-slope form, we get this. On simplifying, we get the equation of the line as x cos omega plus y sin omega is equal to P. This is the normal form of the equation of a line, where P is the normal distance of the line from the origin and omega is the inclination of the normal drawn from the origin to the given line. For example, let us find the equation of the line whose normal distance from the origin is 6 units, and the angle that the normal makes with the positive direction of the x-axis is 30 degrees. Using the normal form, the required equation of the line is under root 3x plus y minus 12 is equal to 0. In this module, you will learn about the general equation of a line and how to reduce it to its other forms. You are already familiar with first-degree equations in two variables. Here, A, B, and C are real constants, such that both A and B are not equal to 0 simultaneously. The graph of an equation of this form is always a straight line. Thus, an equation of the form ax plus by plus c is equal to 0, where a, b and c are real constants, and a and b are never equal to 0 simultaneously, is called the general equation of a line. You are already familiar with the slope-intercept form, and normal form of the equation of a line. Now, let us see how we can reduce the general equation of a line into these forms of the equation. Let us start by reducing the general equation of a line into the slope-intercept form. Consider the general equation of a line such that the constant b is not equal to 0. Rearranging the terms in the general equation, we get by is equal to minus ax minus c. Dividing both the sides of the equation by b, we get y is equal to minus a upon b into x plus minus c upon b. Equation 1 is similar to the slope-intercept form of the equation of a line, where the slope m of the line is given by minus a upon b, and the y-intercept c is given by minus c upon b. Thus, equation 1 represents the slope-intercept form of the equation of a line, with slope equal to minus a upon b and y-intercept equal to minus c upon b. Let us see what happens if the constant b is equal to 0. If b is equal to 0, the general equation is reduced to x is equal to minus c upon a. This equation represents a vertical line with undefined slope and the x-intercept equal to minus c upon a. Now, let us reduce the general equation of a line into the intercept form of the equation of a line. Consider the general equation of a line such that the constant c is not equal to 0. Rearranging the terms in the general equation, we get ax plus by is equal to minus c. Dividing both the sides of the equation by minus c, we get a upon minus c into x plus b upon minus c into y is equal to 1. Rearranging the terms, we get x divided by minus c upon a plus y divided by minus c upon b is equal to 1. Equation 1 is similar to the intercept form of the equation of a line, where the x-intercept a is given by minus c upon a, and the y-intercept b is given by minus c upon b. Thus, equation 1 represents the intercept form of the equation of a line, where the x-intercept is minus c upon a and the y-intercept is minus c upon b. Let us see what happens if the constant c is equal to 0. If c is equal to 0, then the general equation is reduced to ax plus by is equal to 0. This equation represents a line passing through the origin, cutting no intercept on any axis. Let us now reduce the general equation into the normal form of the equation of a line. Consider the general equation of a line. Rearranging the terms in the general equation, we get ax plus by is equal to minus c. Equation 1 is similar to the normal form of the equation of a line. Equating the like terms in equation 1 and the normal form of equation of a line, we get equation 2. From equation 2, we get cos omega is equal to minus AP upon C, and sin omega is equal to minus BP upon C. Let's denote these two equations as equation 3. Substitute these values of sin omega and cos omega in the identity sin square omega plus cos square omega equal to 1. On simplifying, we get the value of P as plus or minus C upon under root A square plus B square. Substituting the value of P in equation 3, we get cos omega is equal to plus or minus A upon under root A square plus B square. And sin omega as plus or minus B upon under root A square plus B square. Substituting the values of cos omega, sin omega and P in the normal form of the equation of a line, we get the general equation of a line in normal form. Note that the constant term on the right-hand side of the equation is always positive, as it is the length of the perpendicular from the origin to the line. In this module, you will learn to find the distance from a point to a line and the distance between two parallel lines. Consider line L and point P in a coordinate plane. The distance from point P to line L is equal to the length of perpendicular PM drawn from point P to line L. Let this distance be D. Let line L be represented by the general equation of a line AX plus BY plus C is equal to 0. Let the given line intersect the X and the Y axis at points Q and R, respectively. The coordinates of point Q are obtained by solving the equation of the line and the equation of the x-axis. That is, y is equal to 0. On solving, we get the coordinates of point Q as minus c upon a, 0. The coordinates of point R are obtained by solving the equation of the line and the equation of the y-axis. That is, x is equal to 0. On solving, we get the coordinates of point R are 0, minus c upon b. Let us join PQ and PR to form triangle PQR. Recall that the area of a triangle is equal to 1/2 of the product of its base and height. Thus, area of triangle PQR is equal to 1/2 of the product of its base QR and height PM. Let this be equation 1. From equation 1, we get distance PM is equal to twice the area of triangle PQR divided by length QR. Let this be equation 2. Recall the formula for the area of a triangle whose vertices are given. Substituting the coordinates of vertices P, Q and R in the formula for the area of triangle and simplifying, we get the area of triangle PQR as 1/2 into modulus of C upon AB into modulus of AX1 plus by1 plus c. Let this be equation 3. Therefore, twice the area of triangle PQR is equal to modulus of C upon AB into modulus of AX1 plus BY1 plus C. Let this be equation 4. Now recall the formula for the distance of a line joining two given points. Substituting the coordinates of Q and R in the distance formula and simplifying, we get the value of QR as modulus of C upon AB into under root A square plus B square. Let this be equation 5. Let us substitute the values of twice the area of triangle PQR and length QR from equations 4 and 5 respectively in equation 2. On simplifying, we get the value of PM as shown. Recall that PM is equal to the distance D from point P to line L. Thus, the distance D of a point x1, y1 from a line AX plus BY plus C is equal to 0 is given by modulus of AX1 plus BY1 plus C divided by under root A square plus B square. Now, let us find the distance between two parallel lines, L1 and L2, in a coordinate plane. Since lines L1 and L2 are parallel, their slopes m must be equal. Thus we represent line L1 as y is equal to mx plus c1 and line L2 as y is equal to mx plus c2 in the slope-intercept form, respectively. Note that the intercepts c1 and c2 must be different. Otherwise, the two lines will overlap and the distance between them will be 0. Let line L1 intersect the x-axis at point P. Since point P lies on the x-axis, its y-coordinate is equal to 0. Substituting this value of y in the equation of line L1, we get the x-coordinate of point P as minus c1 upon m. Therefore, the coordinates of P minus c1 upon m, 0. The distance between lines L1 and L2 is equal to the length of the perpendicular drawn from point P to line L2. Let this distance be d. Recall the formula for the distance of a point from a line. The equation of line L2 in general form is minus mx plus y minus c2 is equal to 0. Comparing the rearranged equation of line L2 with the general equation of a line, we get the values of a, b and c as minus m, 1 and minus c2 respectively. Substituting the coordinates of point P and the values of a, b and c in the formula, we get equation 1 that gives the value of distance d as modulus c1 minus c2 upon under root 1 plus m square. Equation 1 gives the distance between two parallel lines L1 and L2, whose equations are given in the slope-intercept form. Suppose the equation of the parallel lines L1 and L2 are given in the general form as shown. Rearranging the given general equations in slope-intercept form, we get equations 2 and 3 representing lines L1 and L2 as shown. Comparing equations 2 and 3, With the slope-intercept form of the equation of a line, we get the slope of the parallel lines L1 and L2 as minus a upon b, and the values of the y-intercepts of lines L1 and L2 as shown. Recall the formula we derived for the distance between two parallel lines whose slopes and y-intercepts are known. Let us substitute the values of slope m and y-intercepts c1 and c2 in the formula. On simplifying, we get equation 4, which gives the value of d as modulus c1 minus c2 upon under root a square plus b square. Equation 4 gives the distance between two parallel lines L1 and L2 whose equations are given in the general form.